if you choose number 5 as your one question from 5, 6, 7, or 8, congratulations. I think you chose the hardest one. So this has to do a lot of math, so like you better buckle up. Okay, so this one, there is a container, and it's full of water, and they give us the height of the container, so it's 29.8. This app thing is so weird. 29. I'm just trying to write down. Okay, 29.8 centimeters. And we poke a hole somewhere in the container, let's say right here, and then water will come out of it, and we want to maximize this horizontal distance. I'll call that x. Okay, so once we set up our Bernoulli's equation, so P1 plus rho GH1 plus 1/2 rho V1 squared is equal to P2 plus rho GH2 plus 1/2 rho V2 squared. Okay, this app is getting so weird. This used to be the best note-taking app, and then they updated it and made it so much worse. Could have just done nothing. Yeah. So there's our Bernoulli's equation. So then the next step is like choose your 1s and your 2s. So you have to choose your unknown as like one of the variables, either 1 or 2. It doesn't really matter because we're trying to solve for like this height. So I'll just make it 2. So we're looking for H2, right? When we maximize this horizontal distance. And your 1s, you have to choose something that you have enough information. Since we know the height up here, I'll make my 1s at the very top of the container. So some more assumptions you have to make is that the container is like open to the atmosphere, and the hole is also open to the atmosphere. So anytime you're at a point that's open to the atmosphere, right, it's like an open container, it's not closed, the pressure is the atmospheric pressure. So P1 and P2 are 1 atmosphere. So since they're both the same, I can cancel them out on both sides. Another thing you have to do is you have to recognize at like the very top, compared to where your hole is, the water is not moving. So up here, the velocity will be 0. So since the velocity there is 0, right, this whole term is gone. So what we really have is rho GH1 is equal to rho GH2 plus 1/2 rho V2 squared. Okay, so since the rho's in everything, you can cancel it out. So it's really GH1 is equal to GH2 plus 1/2 V2 squared. Okay, so looking at our equation, we know H1, we know little g, we don't know H2, we don't know V2. So since we have 2 unknowns in one equation, that means we probably need another equation to help us solve our system of equations. So since we know it's being launched horizontally, and we want to maximize this horizontal distance, this reminds me of like a horizontally launched projectile question all the way back in Unit 1. So we're going to use like the front of our formal chart back to these free-for-all equations. And I'm just going to copy them all down just so that we can look at them. I'll put them right here. Okay. So since the water is being launched horizontally, that means the initial velocity in the y direction, okay, I'm just trying to write, the y direction is 0 meters per second. And this V2 is our initial x velocity, right? So our initial x velocity, I call that V2. So if we set up our coordinate system, my initial x position can be 0, and my final x position can be x, and my initial y position is H2. My final y position is 0, right, because it's on the ground. Technically, it's all meters. So then using what we did in our coordinate system and our equations, right, I want to use like the easiest one possible. So you can always try to start the easiest one. So if we want to maximize this distance x, right, we have an equation for x, and we know our initial position is 0, and our initial x velocity is v2. So I'll just write that equation, maybe we'll do a different color. So then we got x is equal to our initial x position was 0. So then it's just your initial x velocity v2 times time. But then for time, we have to use our horizontals to solve for time. So we have to do something with our horizontal components. So we don't know the final horizontal velocity, so we can't use that one. Again, there's horizontal velocity, we don't use that one. So you can either use this one or that one. The launch angle, right, is being launched horizontally is 0, but I just want to use that one just because I can. So my final y position is set 0. So then 0 is equal to my initial y position, which is h2. Again, app h2. And my initial y velocity, since it's being launched horizontally, is 0. So this whole term is 0. So that's just h2 plus 1/2, and then our acceleration is negative g t squared. So when I solve for time, right, I'll get negative h2 is equal to negative 1/2 g t squared. Then solving for g, right, multiplied by negative 2, so the negatives can cancel each other out. And then I'll divide by g and take the square root. So it'll be 2h2 divided by g and take the square root. So then if I put it back to my first equation, so then instead of time, I'll put that. So it's x is equal to v2 square root 2h2 over g. Now we're getting a little closer. Right, now we have 2 equations and 2 unknowns so that we can maximize our horizontal distance. So if we want to maximize our horizontal distance, I already have a formula for it. So I'll use this equation from Bernoulli's. I'll solve for v2 and put that into for v2. So I'm going back to this red one up here. And I'm solving for v2. So then I'll subtract gh2 on both sides. So gh1 minus gh2 is equal to 1/2 v2 squared. I'll just factor out g just in case I can. So gh1 minus h2. Then multiply the entire thing by 2 and take the square root to solve for v2. And then I'll put that into this v2 over here. So it ends up being x is equal to square root 2g h1 minus h2 times square root 2h2 over g. So I'll just square root everything and multiply together. So x is square root everything. So 2g h1 minus h2 multiplied by 2h2 over g. So you have a g on top, g on bottom, that's gone. And then I'll just pull out 2 times 2 is 4, right? So I'll put 4. So then I'll pull out the square root of 4, which is 2. So then it'll be x is equal to 2 square root h2 times h1 minus h2. Okay. So then we know h1, right? h1 is 29.8 centimeters. So it'll be x is equal to 2 square root h2, 29.8 minus h2. So then we have one function, right? You can make, so it'd be you can pretend x is y and h2 is x. You can graph it and find the maximum. I have no idea how they make you find the maximum in your pre-cal or geometry or algebra class. I don't know how to do it, but in calculus, you'll know the maximum is where the slope is 0. So the derivative of the function is 0. So if I find this derivative, then I'll set it equal to 0. Then I'll solve for h2, and then I'll check the ends and pretty sure I don't know how Ms. Capet teaches it, but you just find where the derivative is 0, and that is where you have a possible maximum. You can also graph it. So if you're not in calculus, you can just graph it. So then we will get, I guess I'll have to chain rule. I'll just simplify whatever's inside the parentheses. Or I'll just like spread it out so we know the power rule. So 2, 29.8 h2. If you're non-calculus, you can just graph it, minus h2 squared. So then I'll take the derivative of h2, like with respect to x or whatever, however you call it. So then the chain rule, so I'll do like so instead of the square root, I'll just put it under 1/2. So then I'll chain rule, so like I'll multiply. Whoa. So then the derivative, like I guess it'll be like x prime. First derivative of x is 1/2 times 2 is 1. So then I'll do whatever's on the inside. It's the same. So 29.8 h2 minus h2 squared. Then 1/2 now becomes negative 1/2. And then I'll take the derivative of my inside function, which is 29.8 minus 2h2. And then I'll set it equal to 0, because that's where I have a possible maximum. So then I will put that on the bottom. So it'll be like x prime is equal to 29.8 minus 2h2 over square root 29.8 minus h2 squared. And then I'll set it equal to 0. So that means like the top is equal to 0. So 29.8 minus 2h2 is equal to 0. So then that means, so if I'll subtract the 29.8 and then divide by 2 on both sides. So 29.8 divided by 2. So I got 14.9 is h2. Then I'll just put it back into like the denominator and make sure that like it's an actual point in the graph. So then if I do square root 29.8 minus h2 squared. Right, I get a not real answer. That's quite annoying. Wait. Oh, I forgot to do h2. So it's 29.8 times h2. Oops, in our denominator. So if I do 29.8 square root 29.8 times h2 minus that squared, I get a real number. So this number works. Okay, so this could be a possible maximum. So then you gotta make sure it's like reasonable. So it's not 0. It's not bigger than our height. It's I guess this number is like halfway of our height. So it is reasonable for our maximum of like, if we cut the hole right here, right? Because we will have to balance, and we are so bad at basketball. We have to balance our, because if it's lower, the velocity will go higher, because there's more pressure like above it to push it down. But if we're lower, like we hit the ground faster. So it's like halfway is like a mix between high velocity versus high enough height so we stay above the ground. So that 14.9 centimeters is a reasonable answer. And then if you graph it, I also believe you'll get like an upside down parabola, and then the maximum you'll get, the height is 14.9 centimeters as well. So you can graph it, do calculus, do whatever, but this one's really hard, but hopefully that made sense. Okay, so then for part B, once you know for part B, you know everything, right? We know you can solve for that velocity, and you can, right, now it's not even like Bernoulli's equation, right? You know this velocity, you can solve for it. And then you can solve for x using kinematics. Like that's a unit 1. I'm really tired right now and I don't want to do it. But it's just a horizontally launched projectile question. So hopefully you learned something.